Is that okay? This poster. This is not my poster. Can we, what is this? Is this a sponsorship?
No.
Okay, hi. So this talk's mostly going to be a plug about Rust. If you already know something about Rust, you may find it a bit boring, so feel free to go to sleep or hack on your laptop or something. Okay, this was adapted from a very similar talk I gave at my employer, Citrix. So forgive me if any of the Citrix bits get left in. I think I've got the most out. So yes, plug. Those of you who know me may find it kind of surprising that I'm standing here saying, well, this is a good thing, because it's quite new, really. At least it's quite new by my standards. It's only about 4 years old now, this language. And I'm not really known for liking new things. All I can say is I've tried it and I've been impressed. There are things not to like. But in most respects, it's a competent but not particularly novel language. It has one really good novel feature, but the rest is just a collection of the good and competent features you find in other competent languages. Rust's mostly seen as a competitor to C and C++. That's fair. It's certainly fair as far as it goes. But there's a few, there are not that many reasons now to use C or C++ over Rust for an entirely new project. The big one, I guess, is probably dynamic linking, maybe architecture support. But for me, Rust's kind of a high-level language power and its flexibility mean its appeal is wider than that. So I'm going to go on into, firstly, a bit of detail. Oh, that's not worked. I need to do like this. No. Yeah, but they're not doing anything. Sorry, we'll be at a small moment here. Sorry.
Funny.
The PDF viewer has taken control of the screen and won't give it up.
Yes. Okay, so
These buttons.
Yeah.
That's forwards. This is backwards. Okay, that's backwards. Great. Right.
So we got it.
Okay, that's fine, and you can have the laptop back from the PDF viewer at your leisure later. Okay, so I'm going to go into some detail about Rust's one very novel property, which is its approach to memory management. So I want to consider particularly its approach to dynamically allocated memory. Until now, there have basically been two approaches. In lower level languages like C and C++, an assembler, you as the programmer must know whenever memory allocation is occurring. You have to know when it should be freed. You usually have to write explicit code for freeing it. Mistakes in memory management lead to bugs. Often very hard to track down bugs, random memory corruption. There's a number of static checkers and coding conventions which help with this kind of thing, but generally this is one of the biggest problems you face when writing programs in C and C++. The other approach that's currently available is implicit allocation deallocation with a garbage collector. This is very convenient. It's done in languages, most of the languages that you've heard of as high-level languages. It's very convenient for the programmer, but it requires support from a runtime, which is awkward in some environments, and if you mix languages, the runtimes can conflict with each other, and it typically costs performance, sometimes quite a lot of performance. Traditionally, garbage-collected languages are focused on programmer convenience or programming language power rather than performance. So Rust has a different approach. Each object in a Rust program has exactly one owner. And this is not true in these other languages. In C, while arranging, knowing who in what sense owns an object is kind of necessary if you're to do the manual memory management correctly, you're just left to organize that yourself. Typically, advanced, complicated C programs have lots of comments in saying what the ownership rules for the memory are involved. But in Rust, that owner is tracked by the compiler. So for a local variable, the value in that variable is owned by that variable, and it goes out of scope and at the end of the and ceases to have an owner at the end of the block where the variable goes out of scope. In a complex data structure, typically the values in it are owned by some higher up thing in the data structure. So, as I say, C and C++ programmers have typically used fairly kind of formalized notions of ownership, and that's typically written down or implied somehow by the APIs and the internal interfaces, but it's typically not been influenced by the compiler, and if you're lucky, a static checker might spot your mistakes. In Rust, the ownership is core in the language, and so the same rules that you might be used to as an experienced C programmer are expressible in Rust and checked by the compiler. This means sort of you get a thing a bit like garbage collection when an object ceases to have an owner. So this local variable here that we've got, let moot s. So s here is the local variable. S will be allocated by that string from constructor. And at the end of the main, s just goes out of scope. And will be freed. So Rust formalizes this notion of borrowing that you have in C programs. This ampersand is the Rust syntax for borrowing. The compiler checks that the object will outlive its reference. So if we take this example, where are we? Right, so here we have an example of a dangling reference error. This is a standard example of a mistake that C programmers make. It's kind of, you get this in C programs all the time. You allocate something on the stack, and then you return the pointer to the stack object. In Rust, this is a compiler error. And so Rust takes the view that you should write your program so that the compiler can see that everything is correct. Unlike C, where you are basically left to hope. So borrows come in two kinds. There's mutable references and non-mutable ones. And you can have as many immutable references at once, but you can't modify things through it. Mutable references permits modification and gives you exclusive access. And this gets rid of a lot of complicated questions of who owns things, because you can see that if you've borrowed something immutably, then you know it's not going to change under your feet, and the person calling you knows that you're not going to change it. It also gives you thread safety automatically, because the language compiler insists that you only have one mutable reference to the same object at a time, and that means that you can't access the same object through multiple threads simultaneously. So in this example, that's what if we go back 2 slides, we've got this moot s here. If you leave out that moot s, then you say, well, s is here, basically it's just a constant variable. It says, like, we're going to allocate this thing, and we're going to throw it away at the end of the function, but we're not intending to change it in the meantime. This is quite a common programming pattern. You do this all the time in many languages. And you just leave off the moot, and then it says, well, you can't change that because it was a non-mutable variable. If you were to write change ampersand mut s, like we did here, then you get an error saying this variable wasn't supposed to be mutable and you're mutating it. So this makes use after free and double free bugs impossible. Memory leaks are still possible, but you really have to work at it. So Rust programs are safe. You can write bugs, obviously, but you can't randomly corrupt memory. And weirdly, all of this stuff means the compiler can often optimize aggressively because the compiler knows kind of who's looking at any of these variables and knows where all the references are. Often it doesn't need to formally make the things all be where they seem to be, and it can make all sorts of assumptions that nobody else is accessing them. And so the actual machine code you get out of Rust programs sometimes doesn't look very much like the source code. The source code, you have a tendency to build objects by just randomly copying the objects about, where in a C program that would involve a lot of memcopies, whereas in Rust the compiler can look at it and say, oh, well, actually these are all going to be assembled into the same struct at the end, so we'll just like put them there to start with. So apart from the ownership system, it's not, there's nothing new to somebody who's dealt with, other languages you might think of as advanced. If you're used to programming in just like Python and C, then some of this might be new. But these features that I'm about to speak of are in stuff like Haskell and OCaml, kind of Lisp. There's a good selection of the best features from kind of modern practical programming languages. Despite this, it manages to feel relatively familiar, at least to me. I don't know, I'm a bit of a programming languages collector, so maybe that's easier for me. So I'm just going to zoom through a few of these. The syntax, you can see it's a kind of fairly conventional structure of curly braces and keywords and parens and infix expressions and that kind of thing. Looks a lot like C or JavaScript or something. It's not really very controversial. It's statically typed. The compiler will type check it. This is great. You may have heard Haskell or OCaml programmers say once you get the program to type check, it will probably work. Rust, for me, has the same experience. When in the throes of writing some complicated algorithm, you can just try drivel as pseudocode into your editor, and then later, when you've got the basics algorithm written out, you just feed it to the compiler and fix the syntax errors over and over again. And at the end, magically, the program works, despite the fact that you didn't really, think about it properly. And this is just great. I did a program a few months ago that was a mixture of C++ and Perl and Rust, and it was just amazing how different it felt programming, particularly the C++ parts were Boost, so enough said about that. But the Perl parts, you really have to, when you're writing a Perl program, you have to think about everything all at once, because if you just write some bug into it, you're never going to find that bug unless you have a really comprehensive test suite. So all the time, you have to think about everything about your program all at once, and if you kind of leave anything to do later, you have to write a note to yourself, and you have to be really formal and disciplined about everything. It's quite hard work. With the Rust parts, you can just type in any old crap, and it'll, it'll come out in the wash. Brilliant. So Rust has type inference and polymorphism as, some people call this generics. It's more like what you would find in OCaml or Haskell. You don't generally have to write, much of the time, you don't have to write the type annotations. The compiler will figure it out. The polymorphism you see here with this angle bracket, the generics, they're a bit like C++ templates, but they are not mad. C++ templates, don't get me started. This is quite nice. It works really well. I found it a great convenience when programming. Much of the standard library is done in these terms, and you don't get lost in a forest of angle brackets generally. Rust supports dynamic dispatch. That's what C++ calls virtual. Or you can have static dispatch, but in both cases the type checking is done at compile time. So I mentioned safety. Rust is safe by default. So bugs can't corrupt memory. But if you really want to, you can take on full manual control and write unsafe. So I found this was rarely needed, even if you wanted really fast code. I did last year's Advent of Code in Rust as a kind of learning exercise. And at one point I thought, oh, I'll just, this program is taking too long to run. By the way, I've done it. Let's see if I can speed it up. And I decided to hoist a bounds check out of my inner bytecode interpreter loop. And it saved me like 5%, 10% of my execution time on this bytecode interpreter, and it didn't really seem worth the effort I put in. Rust plays well with others, unlike so many other languages nowadays. It has a really good system for speaking C. Speaking directly to C++ is kind of awkward because C++ is so complicated and all that name mangling stuff. So if you want to interface to C++, you tend to write a C file with C functions in that call the, well, that is, you write a C++ file where all the functions you're going to call from Rust are extern C. We've got an example here from one of my own projects. You can see I've had to write unsafe. That's because the Rust compiler can't check that my C++ code is right, or even that I'm calling it properly. It will check the types. We've got this like types here, edges, which is some kind of array, but the compiler can't tell that this len field here that I'm passing to my C++ function is supposed to be the length of the array. Obviously, I write that in my, that's kind of obvious here from declaration, but the compiler can't know it, and so the compiler can't prove that I've passed values here. So that's one of the reasons I have to write unsafe. There's a number of libraries available for gluing your code to Python, say, built on top of this. I can't remember the names offhand, but some of them are surprisingly swish and require a minimum amount of prattling about. So I also want to talk a bit about the attitudes of the Rust project. Now I should say this is an outsider's point of view. I've basically not really contributed to Rust at all. I've written about one Rust library that I think nobody is using. So the most impressive thing for me is that the Rust community doesn't blame Rust programmers for bugs in the programs that people write. So if you're programming in Rust and you write some kind of bug in your program and you think, wouldn't it be nice if somehow, it seems to me I could have, that bug could have been avoided, the compiler could have checked this, or the standard library could have had a more convenient API or something like that. If you go to the Rust people and say, what about this? They have a lot of sympathy with that. That's kind of one of their goals is to save programmers from mistakes. They don't have an attitude of blaming the programmer for mistakes. Humans make mistakes all the time.
But wait until they actually have users.
They've got lots of users.
Well, I don't think so.
Well,
We'll see how fast that attitude changes.
we may see how fast that attitude changes, I guess. The comparison with C is very striking. Right, I mean, I don't know how many people here have read blog postings like this, like what every programmer should know about undefined behavior, part 3 of 3. Right? And that is not what every programmer should know about undefined behavior. That's like some summary. And the whole thing is a complete nightmare, and any time you have some kind of undefined behavior bug in your program, the compiler people will tell you it's your fault. And even if you can explain to them in words of one syllable why this is wrong, I've not seen anybody in the Rust community do this. They all write blog postings saying the opposite kind of thing. The C compiler people are all into, like, your code should be really fast and that's all they care about. But it turns out that your code can be really fast without you having to be blamed for all the bugs in it. So then we're on to, like, interface stability. Now, Rust is a developing language. They do add stuff, but it's taken them quite a while to, this upcoming 1.0 release here, you see 2014, they're already thinking about stability for the long term. They take a quite serious attitude to any kind of breaking change in the language. They have systems for rebuilding the whole of the library ecosystem as far as they can find it and seeing what breaks. But really they don't normally need to use that because normally they're trying, normally they're trying to avoid anything that's a backwards incompatible change at all.
3 years after this, they came up with backwards incompatible changes and had to come up with the idea of epochs.
Right, so that's not to say that they don't change things backwards incompatibly, but as somebody, I'm from the Debian project. We don't do releases. The idea that you would be running modern software, right? My laptop here is on old stable. I found the Rust people, and they're good in this respect. New compilers don't break my shit, as far as I can tell. Also, they don't seem to mind bug reports based on old tooling. Sometimes they might say, well, we think that's probably fixed, but by and large, I haven't had that experience where they say, oh, well, why don't you upgrade to the latest version and see if it does it there too? They really like their error messages. The error messages are, so I mentioned this project I was doing earlier that had a boost part in it. There was like and C++'s error messages are so bad that if you get an error, what you do is you go to the first line number mentioned in the error message and you stare at that line very hard, hoping to intuit what is wrong with it. And if that doesn't work, you revert your change and go back to your last Git commit that compiled, and you try to make the same change again in a way that's not a syntax error. And you can see this in my Git history. Like, I started with the example program from the Boost library, and I gradually mutated it with a series of 3-line changes into the program that I needed it to be.
That is a comment which I do have sympathy for, but it's a criticism of whatever C++ compiler you were using, not of the C++ language.
The problem is the language.
So sometimes it will be, admittedly, some of these things were compiler errors. One of these things I actually discovered was I mistyped a full stop as a comma, and, you get one of these. GCC is particularly bad at this. You get 5 pages of nonsense, and the cursor isn't at that comma. It's somewhere else a bit later. But a lot of it is to do with the language, right? The way that the C++ doesn't really have doesn't have the thing like Haskell's type classes or Rust's traits. It has to kind of synthesize this trait system. Boost synthesizes a trait system out of nothing, and the error messages from that are often very poor. And that's really because they're abusing language features that were intended to do something else in order to catch programmer errors. And well, I applaud their idea that catching programmer errors was a good thing, but having that as a first-class language feature makes getting a good error message out of it quite good. Now, by the time when I was a novice Rust programmer, the error messages would usually write. That is, when it says change this thing, you change the thing, and it would usually, as a novice, it would usually be right. As a more experienced programmer, it's right about half the time, so you do have to have your brain in. But that really helps with the learning curve. So I need to mention code of conduct. They're pretty good about that. They've got, this is on the front page of their, well, it was when I did this talk. I think they've reorganized their website. And they seem to live by it as well. So, what's not to like? What's not to like? So, this one is, so the thing that trips people up mostly is the borrow checker. If you read the internet, everybody hates about Rust. A lot of people end up fighting the borrow checker. Here's an example of a function that's not so easy to write. This just returns a reference to the longest of two borrowed strings. And if you just write it in the obvious way, you get this compiler error message, and you have to decorate it with these lifetimes, which you're basically saying that the return value only lives as long as the shortest of the two inputs. That's annoying occasionally. Also, you can find yourself, if you're an experienced C programmer and you already have a model of who owns what in your head, you can just deploy it, and you'll find that everything just comes out in the wash, and you have no trouble. But if you're not already a C or C++ programmer, you will find you're having to do new work. You will have to be paying attention to what the lifetimes of your objects were anyway, which is a thing that a C programmer has to do all the time, and that, in Python or Haskell you can just ignore.
Doesn't the newer version actually allow you to elide these, at least this particular case of
It's possible that they've fixed this particular case.
It's one of the simpler ones which I think are now automatically handled by
Right, so they are constantly trying to improve this kind of thing. It's difficult, of course, because if you add a new inference to this, they have to make sure that it doesn't cut off avenues for other possible improvements. So they're being a bit slow with that. There are other situations where they've improved the borrow checker as well. They have a thing called lexical lifetimes now, which, or maybe they're called non-lexical lifetimes, I forget, but where you have to spend less of your time kind of making it clear to the compiler when a variable is done with. I think this is a relatively minor problem, at least if you were already buying into the idea of taking control of the lifetime of your objects. And kind of this is the price you're paying for the novel lifetime feature in Rust, which is what gives you the performance compared to other languages. And there's some cool program language theoretical things where it's possible, because the lifetime thing means that it's possible to consume a value. You can write code where it's kind of statically impossible to use an old version of something because the new version has a different type. And the compiler will check that you haven't done that. And there's cool stuff like that you can do in Rust that you can't do in other languages. So kind of, this is the price you're paying. There's one annoyance, kind of serious annoyance, that occurs if you're trying to design a complicated API. It's difficult to define an object type that refers to other pieces itself. Because objects in Rust don't typically have stable addresses, and anyway, there's some complicated mathematical reasons why talking about the lifetime of such a thing is complicated. There's some workarounds in the ecosystem for doing this that are a bit clumsy, but they appear at your kind of API boundary on the inside of your library, just kind of package the whole thing up. So they're tolerable, a bit annoying. Macros. I'm a great fan of macros. Rust does have macros. Not only does it have macros, it has two ways of doing macros. So the more sophisticated macro system is a compile time program transformation written in Rust. So you write some extra Rust code that takes as input the token stream from your program, and it outputs a new token stream. And this has been used to do really awesome stuff that I don't think I've seen in other languages other than maybe with bespoke code generators or Common Lisp. So we've got here this SERDI is a marvelous example of this. This library called SERDI, stands for serialize, deserialize, contains a kind of built-in JSON marshaller, say. So what we're doing here is we say, oh, we'll have SERDI, please, and PS, I want to serialize and deserialize these points, which I've just invented. So you invent the struct point and you say, I'd like to serialize them, and you can just say, oh, well, okay, I'd like to serialize it to JSON, and there you go. There's backends for this for a variety of serialization, deserialization formats, kind of parsers, printers, binary outputs, what have you. And the amazing thing is that all of this is done in a library, right? This syntax here, where we say hash derive, serialize, deserialize, the SERDI library gets the contents of your struct as input, as in the fields of it and their names and stuff like that, and is allowed to generate Rust code to do the marshalling or unmarshalling.
Check for semantic correctness in some way?
Yes. So the JSON parser will take your JSON, input JSON.
No. The correctness of the macro.
The Rust code that comes out of the macro goes into the Rust compiler, and is therefore fully type checked and syntax checked, unless it uses unsafe. I mean, there's probably a little bit of unsafe in SERDI, but
A male programmer like me doesn't feel like a macro. It feels like a function.
Is a function.
it is a bit like a functor, yes. It's implemented here as a macro.
It should not be a syntactic kind of abstraction. It should be a procedural abstraction. Something which takes type information and outputs code in a uniform way.
Yes.
It is not a syntactic transformation. It's really a semantic.
Right. So the macro implementation has access to a library which is essentially the compiler.
Okay.
So it reuses the compiler code to kind of reparse the incoming token stream, and that's how this is even possible. Because otherwise you'd have to write code that knew how to parse Rust struct definitions.
I told you last this slide, I use it in all my serious languages, but there is a risk, which is that you are going to turn it into C++. I mean, until you instantiate your code transformer, you will not see if the output is correct or not, and there may be cases where instantiation fails.
Right. So the point is there may be cases where instantiation fails, which apparently is a problem with C++ templates. I guess that's possible. I've not seen people complaining about it. And SERDI is it's an extremely powerful library with a lot of stuff and a lot of, it's got a lot of front ends and back ends. I would be kind of, if that problem were going to be a big problem, I think it would have come up here. So this general shape of thing is just one example of, the general power of a really good macro system. The problem is it's too much work to write. You can't write a normal, helpful little macro with this, because you need to get with this token stream, and you need to call the compiler's library to turn the thing into what you thought it was, and all the rest of it. And it's just not really convenient. So it does provide another macro system called macro rules. The simpler system is simplified in exactly the wrong places. It's simultaneously overcomplicated and underpowered. I really don't like it. So this example is from one of my projects. This is a debug macro, and we've all written these kind of debug macros. They're like some conditional printf. So this eprint bang is Rust's printf alike. That's the equivalent of fprintf stder, and obviously it's variadic, so we need to kind of take this right-hand side of random token junk and feed it on. Okay, so that kind of okay. There's a lot of clutter in there for a very simple kind of thing to do. And it doesn't even work right. This macro, and in fact it's impossible with macro rules to wrap up ePrint. Because the reasons why are really complicated to explain. I will go into them. And they're to do with the way that macro rules is kind of implemented, and to do with this rule it has about how it takes macro arguments. But the result is that you can't even write a wrapper for printf in this simple macro system. You can write a wrapper for printf that mostly works, but it has bugs. And that's just really annoying. Okay, so the bugs don't generate bad code, they generate compilation errors, but really, no excuse for it. And you know, sometime when I have a spare month, I'll write a new simple macro system that's useful. Maybe sometime when I have a big project that, you know, if I have a big enough project, it'll be worth writing a macro system just for that. Okay, macros. Cargo. Oh my God, Cargo. Right, so I'm a distro person. I'm from Debian. I don't like to download random junk off the internet automatically. I don't like language-specific package managers because, well, I mean, they don't play well with others. They normally fail to solve a lot of problems that the distro package managers solved decades ago. And they really, really, really like to download stuff from the internet automatically. So you can just about hit it over the head and say, I don't want you to download stuff automatically. The Debian people have done that. The Debian Rust team have a thing where they like stick a crowbar into Cargo and have it only read other crates from installed stuff in user share. And that means that the Debian builds of Rust stuff don't access the internet and download random Cargo stuff, which is obviously essential because they couldn't do, because the Debian buildies don't have access to the internet. But if you do that, you discover that all sorts of things don't quite work right. I won't go into all of these details, but it's just so annoying. They've got like an official policy that Cargo should be suitable for running inside some other build system. But anytime you go to them and say, I want to do some kind of weird stuff, they come up with an excuse why what you want to do is a bad idea, rather than, you know, saying, well, I don't think that's a very good way of going about things, but since you've asked, you know, we've provided the following escape hack for people who want to be misguided in that particular way. So, yeah, and the excuses are often based on misunderstandings. I think they've got a little bit of kind of the hegemonizing influence in the Cargo team, and that's a good thing in a build tool. It's in fact a really bad thing in a build tool, because build tools are always the thing you need to mess with somehow. Cargo, yes, sigh. So there's a couple of other problems I want to mention. There is no dynamic linking. They occasionally have kind of hand-wavy discussions about how they intend to do dynamic linking and what the problems would be, and they obviously intend to do it at some point, but not yet. It's not got to the top of their to-do list. The thing that got to the top of their to-do list recently was a lot of work on asynchronous stuff, which was really awesome, and I can't really fault that decision, but it does mean that they still don't have dynamic linking, and that can be a problem. So it might be a problem for security updates if you need to update your library because something right at the bottom has a security vulnerability, except that Rust code tends not to have so many security vulnerabilities because writing in a safe language doesn't. So that's less of a problem, even though the compiler, when it wants to recompile a lot of stuff in release mode, is very slow. So that, I guess, is tolerable, but the executable size problem is only sometimes tolerable, right? If you're shipping like basically one program, and that's the target of your project, then the fact that it's got static copies of everything bundled into it, okay. Mozilla, you know, they ship one web browser, maybe it's got some like little utility program, and that's basically it. If you wanted to write core utils in Rust, forget it. Because each one of those binaries would be like, you know, half a megabyte. And we can't have like 100 half megabyte executables in user bin. So whether this is a problem for your project depends.
There's a lot of people writing re-implementations of core utils in Rust.
Yeah, there are a lot of people rewriting core utils in Rust. Rewriting core utils in a new programming language is an excellent exercise. Great, absolutely. Just, you know, don't expect anybody to ship or run the result.
They do expect
Well,
EXA and the replacements for new fine.
no, I haven't seen any of those things. They're probably up on crates.io, which is the repository of junk that nobody is using. You won't find that stuff in your distro.
Actually, they do. I think some of it is even packaged as binaries as easier.
Well, that's nice. Great, I'm sure that's great. Well, dynamic linking, yes. The other problem is, so for very good reasons, they chose to base their project on LLVM. LLVM is nicely modular. You can do lots of exciting programming languagey stuff with it. But LLVM, originally its kind of heritage is some big corporates who hated the GPL. And the result is that LLVM is a compiler that moves quite quickly and focuses on architectures which have big money behind them. And if your architecture doesn't have big money behind it, or it's a small architecture, like an embedded architecture, then that's not kind of very much on their radar. M68K is not in this supported architectures because there's no M68K backend for LLVM. And current Cephology seems that there probably won't be an M68K backend in LLVM because the M68K community, while they can write a compiler backend, can't keep up with maintaining a compiler backend in LLVM continuously, which is what you have to do, right? You have to constantly be there to fix up all of the test failures when somebody breaks your shit. And this is all not good. It's also a big problem. I mean, Rust would be a really attractive language for embedded programming. The dynamic linking problem is less of a problem, right? You're only making one system image. Performance is good. Memory use is not too bad. Code footprint, well, you can work on that. But if it doesn't support your architecture, then you're stuffed. And you know, this list of architectures is not a great list of all the embedded architectures that you would want to target. And I think this is a big missed opportunity for the Rust project as a whole, and I don't quite know what could be done about it. Well, anyway, despite these difficulties, and, you know, there's minor irritations as well. I haven't listed all those. I've found programming in Rust to be fun, very productive. I mix languages a lot. My record, I think, last time I counted this, was 6 languages in one project. And that tends to throw differences between languages into sharp relief because you have a very different experience in the different parts of the same project and you're constantly switching backwards and forwards. There are many non-trivial programs for which I would now start them in Rust. I would try to avoid starting a new program in C or C++ at this point, if I could totally help it. Even for stuff like Perl or Python or Tcl, I'm a real fan of Tcl, the compile time checking and the performance, but particularly the compile time checking, right? So these interpreted languages have a tendency to explode at runtime because you didn't think of something. With Rust, a bit like in C, you know, C is better at this than Python is, You write a C program, it's more likely to work first time than a Python program, which is frankly shocking. With Rust, it's actually likely to keep working as you feed it new and different input. Whereas the C, if it compiles, right, once you get it to compile, it will probably work on all the input you thought of. Whereas the C one will, you'll feed it something novel, and then it will suddenly stick a corkscrew up its nose and extract its innards the hard way, and you'll discover, mixture of snot and brains all over your desk. Great. Sorry about that. Often I choose a language for its libraries, and the Rust ecosystem, well, there's all this stuff on crates.io, but the quality control is really poor, the libraries are a bit atomized. I don't think I'm going to be choosing Rust for its libraries, apart from maybe Serdi right now. There's probably a couple of other examples where, Rust will turn out to have the best library for the job. But if I'm, mostly writing code of my own, Rust will be high up on my list. So that was all I'd kind of prepared to say. Questions, brickbats? Anyone?
I've heard that Rust is not bootstrappable.
You've heard Rust is not bootstrappable.
It cannot. I understand it's impossible to build a Rust compiler without a Rust compiler.
Yes, well, so this is true of many languages. It seems to be a thing that programming languages people do. Rust is not quite as bad as some of these projects, but yes, getting from zero to a working Rust compiler is not so bad. It's not so easy. Typically, you'll end up cross-building it from some other platform that's got a Rust compiler. That, at least, you can do relatively straightforwardly. Rust seems to be slightly better about not using the most advanced language features in the compiler itself than...
For one version.
Yeah.
If you were trying to bootstrap Rust C, as far as I remember, you can skip every other version.
Well, how long are we talking here? You can skip...
What do you mean?
Well, you say version. Are we talking like 1 month, 1 year?
No, you can skip every other version of Rust C.
Yes, how often are versions coming out?
Every 3 months.
So you can build it with... You have to build it with the one that's no less than 6 months...
Yeah.
No more than 6 months old. Yeah, that's kind of annoying. There are some people who are trying to do a thing that's like a minimal Rust compiler that doesn't do a lot of the checking, which might to do bootstrapping easier, which they've written in, I think, C. I can't remember. This is not perfect. Bootstrapping is annoying, and all programming languages seem to suffer from this problem. At least any language that you'd care to use. Is that it?
I think that one of the slogans of Rust is zero cost abstractions, right?
Zero cost abstractions, yes. I've seen that as a slogan in places. I'm not a huge fan of that slogan because it's basically not possible to have zero cost abstractions, right? So, for example, the Rust generic system, you can choose to have monomorphization, that is like a template system, basically, or you can choose dynamic dispatch. And if you choose monomorphization, you get code bloat, and if you choose dynamic dispatch, you get indirection. But that's inherent in the problem. You're trying to reuse the same code for two purposes, and you're either going to compile it twice and generate two copies, or you're going to use the same copy and pass in some kind of, extra information. I don't think this is new. I wouldn't, if I were a programming language person, I wouldn't try to claim that my language had zero cost abstractions. It is true, however, that Rust code typically is very fast. It's as fast as I would expect the equivalent C code to be, often faster.
Yeah, but my point is that I think that the biggest cost of using something like Rust, at least at the moment, which actually worries me a bit because I love this language. Rust.
Have the microphone.
Rust is like a super very nicely designed language, and but they sell it as a systems programming language, and I think that Rust has the same problem that many other attempts of making alternative systems programming languages for GNU or for Unix, which is what I call the ghetto syndrome. And I explain. We like it or not, the system programming language of Unix and of GNU, which is not Unix, but it's not nothing else, you know, it's not Unix in particular, it is C.
It's not Windows, it's not Unix.
Exactly, it's not Windows. It is not, then the system language will not be C#, it will be not you know, C. So it is C. And it worries me a bit that the people behind languages like Rust, they seems to be missing that point, in the sense that when you create a language like this one, which additional abstractions that what C provides, and then you try to deploy it as a system programming language, or you sell it as one, then you should make an effort to actually become a first-class citizen in the system you want to be a programming language, a system programming language in. What do I mean with this? The lack of dynamic linking, I think that is one expression of it. Not the only one, but I think that is one symptom of that problem. And this ghetto syndrome I'm talking about is that people will very soon, if they did not start yet, people will very soon start to rewrite every system library in existence in Rust, because it is so difficult to interact with the existing libraries that we have in the system. And I'm done.
Reply to your points. Would you want me to reply at the end to all three?
No, yeah, but I have more.
Yeah, okay. Well, so the dynamic linking, absolutely, that is a problem, and they know it's a problem. You know, this is a difficult problem. To try and replace C is obviously a very difficult problem.
Yes.
As for the, ghetto thing, they have, at least the core of the Rust community, have worked really hard on the integration with C. So I've used the C integration facilities, and they're pretty good. I would not hesitate to write a program that was a mixture of C and Rust. So I'm the kind of person who's willing to write programs in 6 languages and like randomly pass data between all of them. But Rust and C go really quite well together. It's not at all difficult. There are multiple easy ways of doing it, and the Rust upstream community are very keen to make mixed language programming good. Now, obviously, they're not yet in a position, that C is to become the dominant thing, but they are definitely, right? And the problem that you're identifying, everybody like, oh, we'll rewrite every system language in Rust. That's just like the enthusiastic fans. Anything like this generates a pile of people who decide it's the best thing since sliced bread and everything else must be consigned to the dustbin, and they start rewriting the entire world in whatever the favorite thing is of the day. And just ignore those people, right? The Rust people, the Rust upstream, the core Rust community, are not really interested in that. There's some things that were worth rewriting in Rust, like, rewriting libSVG in Rust. That was a worthwhile thing to do because libSVG was full of bugs, and they've
replace it, not to have side-to-side implementation.
No, indeed, the SVG upstream is now, they've implemented their library in Rust. Now, because of backward compatibility concerns, they're still supporting, a frozen C version, but that library is the library that C programming, if you run a normal Debian system, that library is the library, this SVG library that you are expected to use, and all your C programs will use it, and it provides the same ABI and API as the previous library. I think maybe there was an ABI bump, but it provides a stable ABI because they've gone to the trouble of writing. So,
but that's why FFI is only half of the picture.
FFI is indeed.
That's what I mean. And in the system,
So I was saying that FFI is only half of the picture, and in the system, glibc, or the libc in a Unix system and glibc in GNU, is not the C library. It's called like that for historical reasons, because C was the implementation language of the system. It's not the C library, it is the system library. And FFI is okay, good, you need it. But also what you need for proper integration and to avoid reinventing the wheel and to avoid being an alien on the system forever is we need a Rust support in glibc. We need glibc to be able to implement, the system level abstractions in the same way that it is doing for C, which will be a subset of the abstractions provided from glibc, also for Rust. And then you will be able to actually replace C as the system programming language, because if you do not do that, you will always be, like a third-class citizen relying on layers on top of that. Or you change the operating system and you write it in Rust. There's a kind of a question here. I don't think that because Rust's FFI works in both directions, right? You can call Rust code from C code. There's no difficulty with that at all. You have to write your Rust library in a way where the C's expectations about memory management are satisfied, but that is not hard because Rust's memory management model is actually quite close to C's. So the difference is just in the level of like checking and safety and stuff. So you can, if you decide that some piece of the system needs to be more rusty, you can start work on that piece. And I think that that glibc will be a little while coming. Because Rust's FFI is so competent, and because the system interfaces tend to have weird memory behaviors that are difficult to express, it will be a little while before we start seeing system calls that are, kind of rusty and where C is a second-class citizen. And also because of architecture support, which I've already mentioned, which means that projects like glibc will be very reluctant to start adding Rust code that isn't backed by corresponding C code. So I think we're a way away from that. So that's a long-term project. I think right now there are places where progress can be made, and if you think of it as you say systems programming language, well that phrase means different things to different people, but there are places where definitely doing more systems programming in Rust rather than C is blocked, and the Rust people they want everybody to conquer, they want to conquer the world, but I think they want to conquer the world unlike some projects that I could mention. They want to conquer the world by making a better thing and making everybody like it so much that why would you do anything else? And they're aware that there are a number of blockers, and it takes time, obviously, developing systems, developing languages, sorting out dynamic linking, architecture support. Those are all real problems.
Well, for the record, this was not a comment.
For the record, this was not a comment like, are you crazy, don't even try, you will manage to do it. I hate that attitude. No, it's the other way around. And actually, I think that I like Rust very much, and I would love, to see it as a real system programming language in GNU. But for that, I think that you should, go to the system libraries. And for example, to add linker support. And not like C++, like, okay, mangling and not mangling. Imagine that you have to mangle, the lifespan and everything, in the symbol name. But hopefully to do it a bit better this time. And hopefully keeping C compatibility backwards, And who knows, maybe in a few years or in 10 years, we can actually turn the GNU from being C-based to Rust-based.
I would love to see that.
That would be great, but I think we're a way off that.
Yeah.
Quite a way off that.
There is,
Do you want to? Could we? Is this other mic working? Let me just.
I'll just share, I think,
Yeah.
It does, yeah.
just one very important question. Why is it called
Can you,
Rust? Why is it called Rust?
I've got no idea.
second,
I think you just need a name. You needed a short name. There are lots of cool puns you can make with Rust. As a name.
who designed it?
Who designed it? I don't have names, I'm afraid. It was a joint effort, right? So the early versions of Rust don't look much like Rust 1.0. They had some very strange different stuff that they threw out after, experiments.
Thanks. So I really like Rust as a language. I've been using it for a few years, but one of my largest concerns with the language is it has no formal specification. You can't write a second compiler backend for Rust because the only specification is what has been implemented on top of LLVM.
Yeah, that is a problem. I know that the Rust people know that it's a problem. I think you should take this with a little bit of a pinch of salt. Have you read any of the academic papers by people who are trying to do static checking of C programs?
Yes.
They typically start with something about how we looked for a formal semantics of C and discovered that there basically isn't a formal semantics for C, and they weren't able to easily write one. And the actual because of C's bizarre provenance-based aliasing rules, which don't appear in any other kind of normal programming language, they had to invent new theoretical concepts to model C's undefined behavior rules, and discovered multiple possible interpretations of those rules, which the standard doesn't distinguish, tell you which to use, and which compilers don't always agree on. So if we're, I think it's fair to compare Rust to C here. Now, C is better in that there's at least a formal syntactical specification. Having programmed a long time in languages with a single dominant implementation, right? I'm an experienced Perl programmer, right? Everybody knows that, not even Emacs can parse Perl. Right? Only Perl can parse Perl. And this turns out not to be a practical problem because Perl is free software. And Rust also is free software, and that makes a huge difference to how important it is that there is a formal specification.
But what I mean, this is why Rust doesn't have undefined behavior.
So because
Because it's not defined.
No, because for the way I looked at it is one of the easiest way to solve the problem that Rust has with the available backends is to port it to GCC. Like, let GCC compile Rust. But that becomes very difficult when there's no formal specification of the syntax of Rust itself.
Right. I think the syntax is not a big deal, right? There's the Rust book has, it's basically full of syntax productions. So I think the syntax, I don't know if that's fully up to date, but the syntax is basically there. The problem is the semantics. Yes, that is a real problem. I think adding a Rust front end to C++ might be, welding. I think I've heard of people who've sort of managed to get a thing like this vaguely working, where they take the front half of Rust C and weld together with the back half of GCC and some kind of totally hideous thing in the middle that converts LLVM IR into something that GCC will accept.
I saw some of that.
There's an experimental GCC frontend, and last week someone sent an email to the GCC mailing list asking for how can I hack it. Or,
The microphone.
No,
There's people watch this later, and it's frustrating if it's not on the stream. We should all be travelling less. We should all be travelling less. So I'm keen to encourage remote participation, and that means that questions should be on the mic.
yeah, there was a bit. So, but I'm trying to my best.
no, I just mentioned that just only last week someone was writing to GCC patches
wanting to hack in the Rust front end. There is a Rust front end for GCC which is experimental, which doesn't work and is sort of abandoned, but looks like some people are getting interested on it.
That's really great. If that goes anywhere, the Rust community will have to get its act together about their specification, because then they'll have two implementations, and that's when you need a specification. Okay, I think we're probably...
Anyone else?
I don't see anybody else, so thank you very much. I'm sorry I took your poster down.